This is an oldie but a goodie, 2002 APC Mechanics 3. I like this one because there's some calculus involved, as well as it's an experimental problem and a design your own experiment problem, so it's going to mix up skills really nicely. So an object of mass this, experiment, look, the older problems are so nice. Look, they all fit on one page. We're going to see that the later the problems get, the more wordy they are. Not to good effect either, by the way. Sorry, sideline. I'm trying to keep each of these videos to like 5 to 10 minutes. On the axis below, sketch u of x. So let's just plot some things. So 0, and then 2, 1, and then 4/3, 2, and then 1. Actually, 4/3 would be a little bit higher there, wouldn't it? Okay. 3, and then now we're at a 0.8, 4, and now at 2/3, 5, and then we're still above half, right? They give you a lot of leeway on those things. And so it's a sketch. I'm going to just draw in that trend then. Okay, clearly a curve. Determine the force. Notice here I didn't get a lot of space here, so I'm just going to go on to a separate sheet of paper. Okay, well, my equation tells me that a conservative force is the negative gradient, right, of the potential energy with respect to the position variable. So there we go. I'm going to put my I hat there. And so remember that negative sign is what everyone always screws up. So this is negative du dx of, let's make this into a nicer form, 4 times 2 plus x to the negative 1 I hat. So let's just do that derivative. Negative sign, 4, bring the negative 1 down, 2 plus x to the negative 2, and then a derivative of what's inside, which is ddx of 2 plus x, which is just going to be 1. Now, you'd never have to show this much work for a derivative on the exam, but I'm just going through it. So this then just is 4 over 2 plus x quantity squared I hat, and there is zero need, folks, in order to multiply that out, not anyone's usefulness. All right, so next, what does it ask us to do? Suppose the object's released from rest, determine the speed of the article at 2. So in other words, this is conservation of energy. Energy at position, released from rest at the origin. So energy the origin is equal to the energy at x equals 2. Work non-conservative is equal to 0. Start with the premise, boom. So this is potential energy at 0 meters is equal to potential energy at 2 meters plus kinetic energy. Final, right? So that's our final, there's our initial. So we can just read those values off. So 2 joules is equal to, at 2 meters, we saw, oh, this is easy, that's 1 joule plus 1/2, and the mass here is 0.5 kilograms, v squared. Oh, how convenient, 1 is equal to 1/4 v squared, v is equal to plus or minus 2 meters per second. Boom, got it. All right. In the laboratory, you were given a glider of mass 0.5 on an air track. Okay, frictionless. The glider is acted on by a force determined in this thing. So that force that we derived here is fine. Your goal is to determine experimentally the validity of your theoretical calculation in part C. So in other words, we need to figure out what the speed is at a particular point. And so this is going to be a little bit harder because we need to know what the velocity at a particular point is when the velocity here is changing constantly. So from the list below, select the additional equipment you'll need to do your experiment by checking the line next to the item. If you need more than one, place the number you need on the line. Right? So briefly explain the procedure we'll use, being explicit the measurements to take. Okay, so here's something I just want to point out, because there's probably, out of these things, something that you don't know what it is. And that is going to be a photogate timer. A photogate timer is a very specific thing that has a beam of light going between 2 posts. And when something cuts that beam of light off, a timer starts. And you can actually have paired photogate timers so that when you go through the next set of photogates, it stops that. We can place them really close together, and that allows us to approximate a final speed. And that's actually how I am going to do this. So here's what I want. I'm going to say I'm going to want to have 2 Photogate timers, a meter stick, and that's it. And so what I'm going to do here is I'm going to set up the 2 Photogates on either side of 2 meters, right? Maybe we'll say like 0.05 meters before and after, okay? And then what we're gonna do is record the time to go through from 1 Photogate to second. And then what we're gonna say is the average velocity in that period would equal 0.1 meters divided by the time between Photogates. And therefore, what we're next going to say is in the region near 2 meters, local linearity of the graph allows me to assume constant force. Therefore, the average velocity in that interval is equal to the instantaneous velocity at the midpoint of the interval, which is where we set it up, because 0.05 meters before and after. And therefore, that's it. That's how we would do it. So nice, simple, straight to the point. The Photogate timer is pretty interesting. You could probably do the same thing with a stopwatch, although you're much more precise with the Photogate timer, but you would just have to make that sort of argument there about why finding the average velocity in the region can help you to find the instantaneous velocity. And if I wanted to do, I could actually even just do a little graph there, right? So if I'm talking about the average velocity in a region, right? Notice it was important to say constant force in that region so that this thing has a constant slope, that the midpoint there is the same thing as the average velocity in that time period.